Today we have section 8.3, day 2. We are constructing confidence intervals for means. And for this, we are going to dive right into an example. It says, a manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies beneath the surface of the viewing screen. Too much tension will tear the mesh. Too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings from a random sample of 20 screens from a single day's production. Construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. All right, some things up front that are relatively important. Okay, we do not know population standard deviation. In inference for this class, it's highly unlikely that we ever do know it. Okay, if we did know population standard deviation, which is examined in some statistics classes, we would be doing a Z interval for means. Okay, Z interval for means do not get addressed in this particular class, letting you know that they do address your calculator functions that do them on your calculator, but if we're dealing with means for this particular class, it's going to be a T interval. Okay, if we're going to construct a T interval, we need to either know that the population distribution is normal, which it does not state population distribution here, or we need to have a sample size of at least 30. In this case, our sample size is 20. Okay, so what do we do if those two things don't happen? Okay, that is going to be one of the variations that occur in this problem that did not happen yesterday. Okay, the second thing is they don't give us summary statistics, they give us raw data. Now, given our calculator skills, that's not a big deal whatsoever at all, but it is a variation from what we talked about yesterday. Okay, when you see the instructions to construct and interpret a confidence interval, unless you're told otherwise, as a free response question, it's assumed that you do the 4-step process. If the only thing you do is state an interval, it is little if no credit whatsoever at all. Part of the AP class is understanding what's implied by certain sets of instructions. All right, so step 1 here is you want to state what it is we're trying to estimate. If you're constructing a confidence interval, it means you're estimating a population proportion. We want to estimate the true mean tension mu of all the video terminals produced this day with 90% confidence. I just want to double check up here in terms of the wording versus this here. Here are the tension readings from a random sample of 20 screens from a single day's production. So, like we talked about many times in this class, we can't make a statement that extrapolates beyond what we sampled from. So if we only have a sample from a single day's production, we can only make a statement about a single day's production. Okay, next. How are we going to accomplish it? What conditions need to be met? Okay, if the conditions are met, we should do a 1-sample T interval to estimate mu. Okay, random. We are told that the data comes from a random sample of 20 screens produced that day. Because we're sampling without replacement, we must assume that there are at least 200 video terminals produced that day. Here's where we get a major variation from what we talked about yesterday. Because the sample size is small, 20, we must check whether it is reasonable if the population distribution is normal, so we examine the sample data. All right, so what we need to do is to make some kind of graph with the sample data. Okay, we could produce a dot plot. We could make a box plot. We could do a normality plot. Okay, actually the fourth option we could do is we could do a histogram. Okay, what we're looking for here is no extreme skewness, no outliers. Okay, if we do not have extreme skewness and we do not have outliers, we don't have reason to doubt the normality of the population. Now, we're not commenting on the normality of the sample. It's what does this tell us about the population. So here they gave us, or it's being shown, a dot plot, a box plot, and a normality plot. These two, if you are working off of one of those, again, you're looking for no apparent outliers, or outliers if you're using this, no extreme skewness. So we don't appear to have extreme skewness or outliers in either one of these guys. If you're working off a normality plot, remember you're looking for a roughly linear line here. If that's not roughly linear, then that gives us reason to doubt the normality. Okay, so how do we word this? Neither the dot plot nor the box plot show strong skewness or any outliers. The normal probability plot looks roughly linear. These graphs give us no reason to doubt the normality of the population. You want to stick to this wording right here. These graphs give us no reason to doubt the normality of the population. That's a generic statement that you want to use here. Now, I know that appears to contradict the using the generic statement, but this hits the context. Okay? Drawing these with it scaled and labeled, that's context. You can make that general statement based off those specifically, contextually specific graphs. Okay, it is not enough just to make a graph of the data on your calculator when assessing normality. You must sketch the graph on your paper to receive credit. You don't have to draw multiple graphs. Any appropriate graph will do. Now, sometimes, if it's a big free response question and there's a lot of stuff going on, they'll give you one or multiples of those graphs. And you just have to comment on, referring to it, what's an important feature. Okay, if they're not given to you, then you're going to have to sketch it. You're going to have to copy it from your calculator onto the page, paying attention to all the details we've talked about many, many times in this class in terms of what you have to have for an appropriate graph to get full credit. Okay, now on to the do part. Now, they didn't give us the sample mean. We're going to have to get that from the raw data. They didn't give us the sample standard deviation. We're going to have to get that from the raw data. We do know that the sample size is 20. We need to get the t-star, and we're going to get that the same way we got the t-star yesterday by using our calculator. You can get it from the table. You're not going to choose to use the table unless you're specifically told to do so. So to get that t-star, I'm going to go stat, not stat, I apologize. Second var to get a distribution. Inverse t, we are doing a 90% confidence interval. That means it's 5% in each tail. That's already set up. 19 degrees of freedom. And our t-star is going to be 1.729. So that's that right there. There is the sample size plugged in. To get the sample mean and standard deviation, stat edit. I already put all the raw data in the calculator in the interest of time. Quit out of there. Stat calc, one variable statistics. Everything's in L1. We're not working off of frequency lists. Calculate. 306.32. There's your sample mean, and you want to use the S sub x, the sample standard deviation, the 36.2. I guess that would be 1 to the 1 decimal place. Then it just becomes order of operations. All right, now in a problem like this, meaning where you're given raw data, if that raw data set has less than 30 items, and we don't know about the normality of the population, then what you need to do is also create one of those graphs. If you're going to be doing one of those graphs in a calculator, the fastest, quickest one to create would be the box plot. So let me go to y equals, I'm in parametric mode from pre-calculus class. Function. y equals, that's clear. Stat plot, let's use the first one, turn it on. I want the box plot option that will show me outliers. X list is L1. Frequency lifts, we either want this to be 1 or blank. I forget which it is for here. That gives us an error message. We'll go back and replace it for 1. And then we will zoom 9 it. And we want a 1 here for... And there's your box plot. Now, as a reminder, you can get all the 5-number summary with all the key numbers, the 5-number summary if you hit trace. There's your median, your Q1, min, etc. All right, as far as the realism of this question on an AP exam, it is certainly 100% fair game to be given a free response question on the AP exam with 20 numbers. The thing that makes this not quite so reasonable is they probably wouldn't be 4-digit numbers like this. If you were to be given a data set that you had to do these types of computations by hands, if it's 20 numbers, they would probably be like 1 or 2-digit numbers. They wouldn't give you 4-digit numbers. But the overall, other than that, one thing we just addressed about the number of digits, this would be a very, very fair game, typical AP free response question, constructing a confidence interval for this, where you would need to get sample mean and sample standard deviation. Oops, sorry, that was out of the screen. Sample mean, sample standard deviation, and have to create one of those 3 graphs by hand. All right, our conclusion. We are 90% confident that the interval from 292.32 to 320.32 millivolts captures the true mean tension of the entire batch of video terminals produced that day. A couple little details here. When you're dealing with means, very often or most of the time there's going to be a unit. You want to make sure you include that unit. Be careful in terms of what you're extrapolating to. We're only extrapolating to the entire batch of video terminals produced that day, because that's the only population that sample came from. All right, circling back a little bit to section 8.1. This would be interpreting the interval. What if they asked you to interpret the level? Interpreting the level means you're interpreting that 90% number. What would that wording look like? If we take many samples of the same size, in this case 20, from this population, about 90% of them will result in an interval that captures the true mean tension of the entire batch of video terminals produced that day. Okay, so what's the generic thing? If you're to take many samples of size, whatever, specific to this problem, you want to have the about, whatever the confidence level is, result in an interval that captures the true mean, that will be generic to all of them, and then specific to this problem, the tension of the mesh wires. Okay, next stop for today. One of the things we looked at with confidence intervals with proportions was how many should you have in your sample size? Well, what does that question look like when you're doing confidence intervals for mean? A wise user of statistics never plans data collection without planning inference at the same time. You can arrange to have both high confidence and a small margin of error by taking enough observations. When a population standard deviation sigma is unknown and the conditions are met, the C% confidence interval for mu is. Again, in this class, we're never going to know population standard deviation. But if you did, which are variations that appear in other stat classes, other stat books, then it would be a Z interval for mean as opposed to a T interval for mean. Okay, that's the same formula we've already discussed. This part right there, that makes up the margin of error. How much are you adding or subtracting? T star is the critical value for confidence level C and degrees of freedom n minus 1. The margin of error is, okay, I already said that. Okay, so these are the difficulties that we need to overcome, and how do we deal with it? To determine the sample size for desired margin of error, it makes sense to set the expression for margin of error less than or equal to the specified value and solve the inequality for n. There are two problems with this approach. We don't know sample standard deviation S sub x because we haven't produced any data yet. The critical value t star depends on the sample size n that we choose. The second problem is more serious. To get the correct value of t star, we need to know sample size. But that's what we're trying to find. There is no easy solution to this problem. So this is how we do, or this is what we do. Okay, one alternative is to come up with a reasonable estimate for a population standard deviation, S, from a similar study that was done in the past, or from a small-scale pilot study. By pretending that S is known, we can use the one-sample z interval for mu. So, if we make that assumption that we know population standard deviation, and we would be making it based on some pilot study or previous study, then we could do the z instead of the t. Once we go to the z instead of the t, then we don't need to know population, we don't need to know sample size. T star is based on sample size, and sample size we're trying to find. So we get that never-ending cycle. So how we deal with the issues that were described in the slide above is we are going to assume a population standard deviation based on a prior study or pilot study, and we are going to, or in combination with that, that allows us to go to a z star instead of a t star. So, here's our example. Researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in laboratory experiments. They would like the estimate to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. A previous study involving this variety of monkeys suggests the standard deviation of cholesterol is about 5 milligrams per deciliter. Obtaining monkeys for research is time-consuming, expensive, and controversial. What is the minimum number of monkeys the researchers will need to get a satisfactory estimate? All right, so if we are going to be doing a 95% confidence interval, for the reasons stated in the last couple slides, we're going to use a z star for a 95% confidence interval, 1.96. The standard deviation number, that has to come from some pilot study. There has to be some estimate prior to creating this or solving this problem to work with. Now, for what we do in this class, it's not like you're going to do a pilot study with monkeys during the AP exam. Okay, they're going to have to tell you something about a pilot study that was done or give you some number to use as an estimate. They told us that was 5. Okay, sample size is what we're looking for. Our margin of error, 1. Again, that will be something similar to the standard deviation from the pilot study, something they'd have to specifically tell you. So now what it comes down to is solving that inequality right there. Now, similar to what I had said when we had this similar type of problem for proportions, a lot of variation in terms of the math class that you've had before you've come here. Whatever your algebra skills are that work best to solve that, that's what you want to go with. Okay, a little bit of a conservative approach. This can be rewritten like that. Multiply both sides, or actually cross multiply. 1.96 times 5 less than or equal to 1 times the square root of n. Well, 1 times the square root of n is just the square root of n. To get at that n, square both sides. Just type that in a calculator, similar to what we did last section. Avoid any intermediate rounding. Get to this stage right here, type that in a calculator all at once. this is always going to round up. You always want to be conservative when it comes to sample size. 96 monkeys is not going to be enough. You need the 97th monkey in order to hit that margin of error of 1. All right, that wraps up what we need to cover for today from section 8.1.